Hello, and welcome to Agrosive Physics. Today is day 112, and what I'd like to do today is give you an overview of the static electricity chapter. And we've discussed quite a bit about static electricity in the past few lessons. In fact, we started with the discussion of the Van de Graaff generator versus the Tesla coil. Now, the Van de Graaff generator worked by friction. It allowed friction to pull off excess charges and create a very large static charge on the sphere at the top of the Van de Graaff generator. The Tesla coil worked with a series of capacitors and transformers that stepped it up to a very high voltage and stored charge in the capacitor. That was released and was able to form sparks from the metal tip of the Tesla coil. After we talked about that, we discussed conservation of charge. Now, the total charge of a system needs to be constant. It can't change. If we touch objects together, they're going to transfer charge to reach a state of equilibrium. But we have to realize that electrons don't break up into smaller pieces. So if we have an odd amount between two things, for example, +7 is our total charge. Well, one would get 3 and one would get 4. You're not going to have 3.5 on each. That being said, we discussed the fact that the charge of an electron and proton are 1.6 times 10 to the negative 19 coulombs. We can't use +1 and -1 like we did in chemistry because many of our equations are based upon the actual charge in the metric system, which is based on the coulomb. After that, we discussed 3 different methods of charging. We discussed the fact that you can charge objects by friction, by conduction, and by induction. When we charge by friction, the amount of we're basically rubbing the excess electrons off of one and transferring it to another. The triboelectric series will allow us to determine which object will become positive and which will become negative. When we charge by conduction, we're physically touching an object to another, a charged object to another object, and the excess electrons will either move from the charged object to the neutral one or from the neutral to the charged object, depending upon the original charge. Conduction decreases the strength of the original charged object, and they both share the same sign in terms of the charge. An electroscope can be used to detect charges, and the relative strength is based on how far apart the leaves are on a foil leaf electroscope, or how far the arm moves on a straight standard electrical charge electroscope. Another way we can charge is by induction, and that's when you bring an object that's charged near another object, you ground the original object, and because of charge redistribution, the charge either moves into ground or from ground into the neutral object. So you charge by induction and don't change the charge of the original object, and you get the opposite charge at the end. We then discuss Coulomb's law, which is Q1 times Q2 over R squared, K being the electrostatic constant, which is 9 times 10 to the 9, Newton meter squared over Coulomb squared. The sign of the Coulomb's law force will allow us to tell whether or not it's attractive or repulsive. If it's negative, it's attractive. If it's positive, it's repulsive. We did a number of sample problems dealing with Coulomb's law and then discussed the electric field, which is the region around a charged object that affects other charges within the field. We have 2 equations for that, E equals F over Q and KQ over R squared. If we have F over Q, the Q is the test charge, and KQ over R squared, that is the charge of the source producing the electric field. Electric fields are vectors, so we have to worry about vector addition if we have multiple sources. We then discussed a visual representation of the electric field and talked about field lines, and how the number of lines represent the strength of the field, the proximity of the lines represent the strength of the field, and the fact that we always use a positive test charge when determining the direction of the field. What would a proton do? We talked about what different fields look like depending upon whether or not you have a single point source, 2 unlike charges, 2 like charges, or even parallel plates. After that, we discussed electric potential, which is a scalar quantity, and more importantly, the potential difference between 2 points in a field. When you have the electric potential, that is also known as voltage, and we have voltage, which is a common term that most people are familiar with when dealing with electricity. We talked about parallel plate capacitors and how we can use the equation V equals ED to solve for the electric field inside, which is uniform because they're parallel plates. We then discussed Millikan's oil drop experiment and how he was able to determine the charge of an electron by putting oil droplets inside an electric field and observing their motion. When they were traveling at a constant rate downward, he knew that the gravitational force and the electric force were both the same, and he was able to deduce the charge on each of the oil drops. From there, he found that the oil drops all had a multiple of the base of 1.6 times 10 to the negative 19 coulombs, which he determined to be the electric charge. Now, after that, we did some sample problems, and we're up till today. Now, I would like at this point to solve some assessment type problems, some multiple choice type problems. So we'll take out the whiteboard and solve some sample problems that you may face in an assessment at the end of a chapter, at a state assessment in the near future. Thank you. Okay, it's time to look at some sample multiple choice problems for a state assessment. And our first one is about two charges that have a force on them of 2 times 10 to the negative 5 newtons. They're a distance of 2 meters to start, and that is brought to 1 meter. So effectively, their R is cut in half. Now, how does that affect forces? Well, if our equation is KQ over R squared, which is Coulomb's law, K is constant, Q is constant, the other Q is constant, and we half square the R, 1 on the top, 1/4 on the bottom, it's 4 times bigger. So that means we're going to take that 2 times 10 to the negative 5 and multiply it by 4. 2e negative 5 times 4 is 8e negative 5. So my choices are going to be 8 times 10 to the negative 5 newtons, which is choice 3. All right, the second one. Do as many as we can on this page before we flip. Total amount of work required to move a proton through a potential difference of 100 volts. Well, the equation we have is V equals W over Q. We have 100 volts. We want to find the work, and we have a proton, and the charge of a proton is 1.6 times 10 to the negative 19 coulombs. So 100 times 1.6 to the negative 19 is 1.6 times 10 to the negative 17 coulombs. So my choice is going to be 2. All right, number 3. Two parallel plates are separated by a distance of 1 times 10 to the negative 3 meters and has a potential difference of 12 volts. We have an alpha particle moving with a positive charge moving toward point P. So we have something that looks like this, and the positive charge moving toward point P. We have pluses up here. We have minuses down there. The equation is going to be VED. So 12 volts is V. We have a distance of 1.0 times 10 to the negative 3 meters. So we do 12 divided by that. 1e negative 3. And we get 12,000. And it's an electric field, so it's newtons per coulomb. So 12,000 is 1, 2, 3, 4. So 1.2 times 10 to the 4 newtons per coulomb. They're listing all the answers in scientific notation. So we have this as our choice. But unfortunately, there's 2. So the top plate is A and the bottom plate is B. And we always define the electric field as what would a proton do. And a proton will be pushed downward. So it would be toward plate B, which is choice 4. All right, let's see if we can fit one more on this page before we reset. What's the magnitude of the electric field intensity where an electron experiences a 1.6 Newton force? Well, our equation's E equals F over Q. Force is 1.6, I'm sorry. It says 1.0 Newton. Oh, 1.0 Newton. I just misread it. And it's an electron, so it's 1.6 times 10 to the negative 19 coulombs. 1 divided by 1.6 to the negative 19 is 6.25 to the 18. 6.25 times 10 to the 18 newtons per coulomb. Unfortunately, none of those match, but 6.3 is the closest value, so they must have rounded that. And that's choice 3. So let me reset, and we'll look at the next few. Hopefully we can fit another 4. All right, let's look at question 5 now. 5 said, what's the magnitude of the electrostatic force between 2 electrons separated by a distance of 1 times 10 to the negative 8 meters? So, equations, Coulomb's law, F equals K, QQ over R squared. So 9 times 10 to the 9. Electron is 1.6 to the negative 19. And since there are 2 of them, I'm going to square it. All over 1 times 10 to the negative 8 squared. If you notice, I didn't put units on this because it's a part 1. It's multiple choice. And we're not going to check your work for the multiple choice. So substituting with units is important. But in terms of speed for a state assessment, it might behoove you to skip the units for this section so that you can move a little quicker through it. You have more time for the part 2s. But that's really up to you. And what I'm getting is, let's see, 99 times 1.6 up. I had positive 19. My answer did not match what I got. I hit the wrong button, negative 19 squared. That's going to be a little better. Divided by 1 e negative 8 squared. I'm getting 2.3 times 10 to the negative 12 newtons per, no, newtons. 2.3 to the negative 12 is choice 3. There you go. So what I did wrong is I didn't have the negative sign. I went too quickly, missed the negative sign, and my answer didn't match. Fortunately, it didn't match because then I knew my mistake. All right, we have a graph of work versus charge. And what does the slope represent? Well, slope is change in y, which is w, over change in x, which is q. So, work per unit charge. I guess that's V equals W over Q. So that's voltage, potential difference. So that's choice 2, potential diff. Let's look at 7. All right, what's the magnitude of the electric force acting on an electron located in an electric field with an intensity of 5 to the 3rd newtons per coulomb? So Z equals F over Q. Now, of course, I have all the formulas memorized, and if you need to look, you look in the electricity section of the reference table. 5 times 10 to the 3 newtons per coulomb equals F, and the electron's 1.6 to the negative 19 coulombs. So 5 to the 3rd, 5e3, times 1.6 e negative 19, and I get 8 times 10 to the negative 16 newtons. And that is choice, well, it should be choice 2, but choice 2 doesn't have newtons on it. I'm sure that's just a typo. Every other unit in the choices has an N, but there's no other number that matches. So I'm going to go with 2. I'm going to put a star, but I'm pretty sure that's just a typo. All right, we got 3 to go in this practice set. We have 8 coming up. How much energy is needed to move 1 electron through a potential difference of 1 times 10 to the 2 volts? V is W over Q. So we have 1 times 10 to the 2 volts equals W. And an electron is 1.6 times 10 to the negative 19 coulombs. So 100, 1e2, times 1.6 e negative 19, and I get 1.6 times 10 to the negative 17 joules. And that's choice 4. Now, if this were me, I would then ask you how fast does the electron move, and you would have had to use 1/2 mv squared from that, this being the Ke. But I didn't make that question. All right, number 9. We have Millikan's oil drop experiment. All right, what's the magnitude of the electric field intensity when this oil drop was in equilibrium? Well, we know that E equals F over Q, and they're telling us that the mass is 3.2 times 10 to the negative 14 kilograms, and I know the force is going to be the force of gravity, so multiply that by 9.8. And then we're going to divide that by, it has a charge of 1.6 times 10 to the negative 18 coulombs. So it probably has 10 extra electrons. So 3.2 e negative 14 times 9.8, that's the force of gravity. Divide that by 1.6 e negative 18. And you get 196,000 newtons per coulomb. Now, none of the numbers match that, so we're going to round it. So let me write in scientific notation. 1, 2, 3, 4, 5. 1.96 times 10 to the 5 newtons per coulomb. And they're going to say that's 2, so they round it up to 2. So it's choice 2. Look at that. Now, finally, number 10. Let's see what we have. Electrostatic force is F when they are 0.1 meter, and then we move them to 0.05 meter. So 1 to 0.05, that's half, right? 0.1 to 0.05, that's why. Yeah, it's 2. So we made it half as big, so that's going to make the force 4 times bigger. So it's going to be 4F, because we do 1/2 squared on the bottom and 1, 1, 1 on the top. And that means 4F. Now, 2 positive point charges means they repel. So the choice is going to be 3. 4F and repel, because they're like charges. Got to watch out for the 0.1. I did 1 divided by 0.05 and got 20. All right, so that's your overview of static electricity, some practice multiple choice problems. And after this, you'll probably take an assessment in class. Then we'll move on to current electricity next.